Okay, people, today we are going to explain details about the calculations that you have to do in order to complete the assignment. The second part, the first part, this is just one single degree of freedom. You should be able to solve it just for the second, okay? And Engineer Isaac also did a short video on some of the results that we obtained last year with the same equipment. So my plan is in the fourth week, when you come to the university, we repeat this test. Okay, so we will be able to compare your results with the result from the forced vibration in the lab. Okay, probably we will have time to do a short experiment on hydrodynamics. Let's see what happens, okay? Hopefully about waves or something like that. But that's the idea, okay? And also I'm going to explain about that some details about the, not much than details, about the second part, the last part of the homework, which is about the same model, but in the forced case, okay? So let's do it. Isaac, can you see my full screen?
Not yet.
Full screen?
Not yet.
Now?
Now it's okay.
Okay, thank you. So this is what we explained yesterday or on last week, okay? This is the system that I want you to analyze, okay? In this case, we are going to model. That's what is class. It's a very extremely important when we do this type of analysis, okay? Because usually we cannot analyze the system as it really is, okay? So we have to simplify somehow, okay? So in this case, these elements are very thin, okay? And we assume them as they were completely massless. And here, you will see in a minute a photograph of the system. Here we included some weight, okay? Some weights, different weights. So this is the model that we are going to be analyzing again. Okay, so the foundation moves and we know this motion, okay? And then these pieces of legs are going to be modeled as springs. But I put it horizontally because the motion is in this direction. So even though they are vertical, the stiffness acts in this direction, okay? We have two, so we have to say something because these two will be represented by one here. Now, in here, probably, and not I don't think anybody can see, there is some damping here, okay? And that damping is represented in a very simple way, very, very, very simple way as a linear viscous damper, okay? Then we have the mass, which is this, basically this one. Now, if you want, you could take piece of this, piece of that, and put it into here. But that I think is just too much. Let's take just the value of this in here, and that's it. Now, if this moves, okay, you cannot expect the second story to move the same. So the second story is the second degree of freedom. And to specify its motion, we declare a second variable, U2. And similarly, there is a third story of this building, and the motion of this, the third story is U3. So at the end, we're going to have 3 degrees of freedom, and in general, this is what we are going to analyze. Okay, so let's see a little bit of details in here. Okay, this is something that is included in the formulation of the problem. Okay, so here I have a clamped lower end of this. Let's call it it's a beam. Okay, And here, it connects to the first story, okay? And the way this is modeled, okay, each one of these is this. Simple model, okay? And this is not mine, okay? We read in the literature, and the simple model that I use is to consider this, each one of these legs as they were clamped in the lower end and guided in the upper. Okay, so it's clamped here and guided here. Okay, so if we have something like this, okay, here we have it guided. So it's like having something like this. I'm sorry. Jesus Christ. Oh, yeah, right. This is not the one that I'm using. This is the one that I'm using. Okay, thanks. So it's up here. And then it allows the upper part to move in this direction. Okay, but we assume that this connection is very rigid. So it's like this and like that. And let's suppose we have a connection here. So this is very rigid. The connection is very rigid. So this 90 degrees angle is kept during the motion. Okay. So when it moves to the right, so it's like doing this type of motion, like this and here, like that. Okay. How do they calculate this? Well, what they do is they apply a force. And what they do is they calculate the deflection delta in the horizontal direction. Okay. So this is a very simple problem that you can solve. This is a indeterminate problem because here I have two reactions, and here you also have the bending moment is unknown because there is no possibility of rotation. Okay, so but you can solve it, and at the end you can obtain the deflection or the axial motion and evaluate in this point here, and that would be delta. And then in similar way as we have done before, we calculate the quotient F divided by delta, and that's by definition K of U. And that's the result that we obtain. Okay, so according to the boundary conditions, you could obtain different values of this effective K. In this case, that's the result that we obtain. Okay, now, of course, E is Young modulus, I sub C is inertia, and L is the length. So in this case, the length is 400 millimeters. So it's 40 centimeters from here to there. Okay, now the inertia, we have to be careful because let me draw in perspective, okay? This is from a flat bar like this, right? Okay, and here we have the connection for each one of the stories. Okay, so if we make a cut here, this is the section. This is the neutral axis. So the height is the thickness of the flat bar, and B is the other dimension. So with these two dimensions, you can calculate the inertia. This is steel, common steel, and this is the length again, so we are okay. Just to be, any questions about these people? Any questions? Any questions? No, okay. Now, let me go back a little bit here. See, we're using, let me change color. I have a spring for this and another spring for that, okay? So each one of these is, I'm sorry, has this stiffness, 12 EI sub C divided by L cubed, okay? Since in this case, these two are in series or in parallel, anybody? These two springs will be in series or in parallel, anybody? People, I need to know that you are awake. That's what I'm asking you. Parallel. That in parallel. So the K adds or subtract. That's a good question, huh? Adds or subtracts. Let's analyze. Let's analyze this. Let's avoid being just by memory, saying something by memory. Okay. Where am I? Here. Okay, so it's like I have this column and I have this column, right? So there is a force here and the same force applies here. If I had only one leg, I would go up to here. But if I apply the same force, but I have two legs now, okay, the deflection will be half. That means that the effective stiffness will be the summation, okay? So if you have like if half force here and half force here, you're gonna have delta over 2 here and delta over 2 here from the comparing with the original case, okay? So in this case, you are gonna have to add, okay? So add, since these are in parallel, add case. Questions? So let me go back. So you have to calculate for each leg KU. Double that, that's going to be the effective K between each one of these stories of the building. Okay, so here, this is going to be the summation of the K, this from this side plus the K from this side, which are equal. So it's twice. Okay. Questions, no questions. Okay. Okay, so in this way, you could completely model the system. Okay. And eventually you're going to have something like this. Okay. So you're going to have a mass K matrix zero vector. So all of these with these factors of 2 and all of that are going to be in here. That should take you to calculate natural frequencies and mode shapes. Okay. No questions. Ms. Pincay, are you okay? Are you with me, Ms. Pincay?
Yes, I have to process that information.
Okay. Mr. Galarza, how do you feel?
I just have a question, doctor. What about the damping? Should we consider the damping?
Remember, this is free oscillation.
All right.
Okay, so free oscillation, we're interested in natural frequency and mode shapes. So right now, we are not going to include damping yet.
All right.
In a few minutes, I will include it. Because in the next step, we're going to go to forced vibration. And of course, if we do not include damping, then the response at resonance will be infinite. And we, of course, we don't expect something like that in real life.
Yeah.
Okay, why don't we do this? Okay, everybody, give me the equation of motion of the, okay, Astudillo, Arnold. What's your last name, Arnold?
Sorry, Manrique.
Enrique, Galarza, and Jimenez. You deduce the motion equation of U1. Mr. Jimenez, Ramon, and Pincay and Delgado, you do the second one. And Mr. Zamora, Sayo, Freire, and Carrillo, you do the motion equation of the third one. Okay, I'll give you a couple of minutes. I have two more here. Oh yeah, I have more people here. Zambrano and Matias, you do first. Matute and Lopez, you do two. Sayo, did I assign you something?
The third.
Okay, good. Okay, go on. So let's agree on the notation, okay? Because I don't want to have everybody to have a different notation. Okay, so let's see. Here we're gonna go. These are going to be K1. This is going to be K2. This is going to be K3. Okay. Remember, this is free vibration, no damping, no excitation, because we're interested only in free oscillation. So each one of the groups will give me one equation of motion. There is somebody in the waiting room. If you have it, raise your hand so I can ask you to share with everybody. your result. Ms. Lopez, are you there? Ms. Lopez?
Yes, doctor, I am here.
Okay. Mr. Matute, are you there? Can hear you. Could you please check your microphone? Miss Matias, are you here? Are you there? Miss Matias? Okay. Mr. Zambrano, are you there?
Yes, doctor, I'm here.
Miss Vega, are you there?
Yes, doctor.
You are in La Manar, right?
No, I am in Guayaquil.
Oh, wow. Mr. Carrillo, are you there?
Yes, in Guayaquil. Doctor, I have a question. This system
Yeah.
is similar, have the example, the ship in lab. We have the two results.
It's not quite.
No way.
No, because this is different. This is just the 3 degrees of freedom are longitudinal displacements. In the case of the other, you have
Vertical.
vertical, and the other degree of freedom was rotation. So there's some similarity, but that's all.
Process.
Yeah.
Thank you.
No problem. No problem. Okay. Anybody? Come on, give me the question for the first mass. Mr. Delgado, come on, give me something. I need to write.
Okay, for the mass 2, I have
Okay.
mass 2, you double that.
Okay.
Plus U2 to K, the K2 plus K3.
Like
Yes.
that?
Yes. Minus K2 U1. And minus K3 U3.
Did anybody else did the second mass?
Okay.
Mr. Zamora, what mass did you do? Do you agree with this?
Mass 3, doctor.
Oh, you're mass 3. Who did mass 2? Mr. Jimenez, you did mass 2? Do you have the same result?
Yes, doctor.
Okay.
I agree.
I'm not saying it's correct because I don't have the time to check. Ms. Freire, you have, which one do you have?
Mass 3.
Okay, go on, Ms. Freire.
K3 U2
K3
minus
U2.
U3 and plus K3 U2 minus U3.
I don't get it. Let me erase everything because I got confused. Okay, let's do it again. Go on.
K3
K3
multiplying by U2 minus U3.
like this.
Yes.
Okay. And equal to 0.
No, plus K3 multiplying U2 minus U3. Well, was twice the same thing.
So it's, come on, I get confused here. Up to here
It's
only.
the same. It's the same.
So that's it. So that's equal to 0. Is that correct? Isayo, did you check this? Do you
No,
agree with this?
it's twice that thing.
Okay, but
Twice
where
K.
to? I think there is a problem here. I think it's minus here.
Yes, I have minus.
Yes, I have mine.
I have minus. Be careful. Okay, and finally, somebody from the first one.
I have
Okay, go on.
minus 1 multiplied by U1 double dot
Okay, plus.
plus K1 plus K2 multiply U1
Okay,
minus K2 multiply U2 equals 0.
that's it. Okay, so here we have it. I'm not saying this is correct. You should check it. Okay, please practice. Okay, if you don't get the same, try to check. Okay, because during the test, everybody will do it independently. Okay, now, next step is to establish like this. Something like this. There. So we said that the determinant of D equal to 0. And for doing this, for example, you need Excel because this is a 3 by 3. And I don't know if somebody wants to do it by hand. Okay, so what I do is in Excel, okay, that's why I want you to do these modules in Excel. See, what I do is, you can do something different, but that's what I do. See, I assume a value of omega. So in this cell, I put a value for omega. I'm just assuming a value. And in here, in this part of the table, see, I implement this. And of course, this value depends on omega. And now here, I ask Excel to give me the determinant. Do you remember does anybody remember the name of the function to calculate the determinant in Excel? Does anybody remember? No? Okay, then you have to figure it out. But immediately you will have here a value depending on the value that you assume. You assume here. What you can do is you can start doing something like this. It's just assume values. And from here, you will see that it still keeps increasing. And then the other side is go to the other way. So here you can identify 0 crossings. So you're gonna have 3 0 crossings, and what you have to do is you have to be more detailed around these regions, 1, 2, 3, in order to determine the values of the determinant. Oh, I'm sorry, the frequency which made the determinant equal to 0. Okay. After that, oh, I need another page. Let me reproduce this because I need one more. Ooh. Okay. Remember the process. Process is that you have a 3x3.
Sharing your screen.
You have a 3x3. You got U1, U2, U3. Now, inside here, you have omega squared. Now I'm going to change color.
Doctor, you're not sharing your screen.
Oh, okay. Thank you. Thank you. Every time I do something wrong, tell me, because otherwise we will waste time. Okay. Thank you. Okay, here. How about now?
Yeah, it's okay.
Thank you. Thank you. Who spoke? Who said something? I don't recognize the voices. That's the problem. With red, at the moment that I replace this omega by one of the natural frequencies that we already obtained, here I have omega 01, omega 02, and omega 03. If I replace any of these in here, immediately the determinant of this is 0. So this system is linearly dependent. That means that we are not able to solve it just like that. What do? We said, okay, we have to cross one equation. Forget about it. And what we have to do is we have to accept that we are not going to find values of U1 and U2 and U3. So what we do is we divide the whole system, okay? We divide it, for example, by U1. So we're going to have only two equations. Here, we are replacing by one of these, and here, the first one is going to be this by that. So it's going to be 1. The second is going to be that, and the third is going to be like that. So this is known, this is 1, and this is multiplied by these two elements of this matrix. So this product will give us known values. So they become independent term, and we move it to the right. So we have this part here. It's going to be a 2 by 2. Okay, so this element is in the first row, in the second column. This one here is going to be 1, 3. This here is 2, 2. And this is 2, 3. They are multiplied by U2 bar and U1 bar. And these are the ratios between U2 and U1. And here, on the right-hand side, I move these values multiplied by 1. So the first one is going to be D11, and the second is going to be D second row, first column. You see, all of this process, you can do it using Excel. That's why I need you to do this module. And finally, you can obtain the mode shape. The mode shape is going to be each one of these divided by U1. So of course, this is 1. And the other is going to be these values that you obtain solving this 2 by 2 system. And this is for any. So you start replacing this by one of the frequencies, and the result is going to be the mode shape which goes with that frequency. Okay? Questions, people? Questions? Questions? No? Okay, before we go to the break, okay, let's go to this here. So let's think that this is a straight line for the mass 1, for the mass 2, and the mass 3. Okay, now, the first mode shape, see, the 3 values will have the same sign. So this will be 1, this will be something different, and this one is going to be something different. So we can draw something like this, and this will be the mode shape number 1. How about the second one, people? What's going to be the difference with the second one? Anybody? The first value will be 1 again, because this is always 1. What about the second one, the second value? How is it going to change? Exactly, to the left. It's going to be negative. And the third one is going to be positive or negative, the third one.
Will be positive.
No,
Negative.
it's going to be negative. I don't know if it's going to be like this, but more or less that's it's going to be. So it's going to be 1 here, some negative value, and also some negative value. But you have only 1 change in sign. So we go from 0 to 1, negative and negative. And finally, let's change color. Let's go to Barcelona. And then we're going to have 2 sign changes. So we go from here, maybe up to here, and from here back to positive. So we're going to have 1 here, a negative value, and a positive value here. So this is for the third mode shape. Sometimes it gets some messy. So we have to be careful with the number of sign changes, okay? Also, in some cases, you could have close natural frequencies. And in those cases, it is possible that the mode shapes are very close or something like that, right? So try to be as precise as you can as far as the calculations of natural frequency is concerned, okay? Any questions, people, before we go to the break? No? Okay. In that case, we're going to have a break here. Okay, let's have a 5-minute break. Isaac, you can stop recording. 5-minute break.